Hi everyone, welcome to CSCE 317 Lecture 9. Hope you're all staying healthy and coping with the isolation. I also hope you got an opportunity to enjoy the great weather we had this past weekend and today. Today's lecture will mostly cover the next lab, which we posted to Dropbox earlier this afternoon, and it is due next Tuesday. This lab will use the same tools that we developed for the last lab that allow you to write code for a virtual 328p and a virtual SPI channel. But this time the SPI transactions will be a little more complex. Before we begin, I wanted to clarify some terminology because we may not have been entirely consistent in previous lectures with these terms, and it's important that we're precise here in order to avoid confusion when we start getting into these more complex SPI transactions. So as I'm sure you're aware by now, if we assume that there's one master and one slave, then all SPI communication is performed as a series of exchanges where the master sends a byte to the slave and the slave simultaneously sends a byte back to the master. In some cases, one of these bytes is a dummy byte, meaning that it's not meant to be read, so it just contains placeholder bits. The master sends its byte out through MOSI, and the slave sends its byte out through MISO. An SPI transaction, on the other hand, is all the exchanges that occur while the slave select or chip select is asserted, which obviously can be one or more exchanges. In our case, it's always two or more exchanges. So, for instance, if we perform an SPI read operation, you can easily see where the transaction begins and ends because that is where the chip select or slave select becomes asserted and then deasserted. And remember, chip select is active low, so it's asserted when it's 0, right? So when chip select goes to 0, you start the transaction. When it goes to 1, you end the transaction. This transaction is comprised of two exchanges. How do we know that? Well, we only know that by counting the number of clock cycles that have elapsed during the transaction. In this case, there are 16 clock cycles, and we know that each exchange takes 8 cycles. So there were two exchanges that take place. In this case, the first exchange is where the master sends 2 flags as well as an address to the slave. The flags indicate that it's doing a single read operation. The second transaction is the slave sending the contents of the requested register back to the master. So in the first exchange, the master sends the slave a read address and the slave sends the master a dummy. And then in the second exchange, the master sends the slave a dummy and the slave sends the master the contents of the register that the master wants to read. If you're doing a multiple read, you will have one transaction and more than 2 exchanges. Again, we know this simply because there's 8 times 3, 24 cycles that occur while the slave select or the chip select is low. The first 8 are, again, the master sending the slave the address, and then the second 2 exchanges are the slave sending 2 bytes back to the master. Generally, these 2 bytes are consecutive registers beginning with the address specified in the first exchange. Okay, so that will become relevant for this lab. In lab 3, your objective is to connect your virtual 328p CPU to 2 peripherals on one SPI bus. By one SPI bus, I mean that both the peripherals share the same MOSI, MISO, and clock connections. Our 2 peripherals are named VD002 and VD003, with the VD standing for virtual device. The reason we start at 2 is because we had VD001 in the previous lab. On the left is our VD002, and it's a sensor that in the picture makes it look like a little bit like a mini boombox, but it's actually a picture of an ultrasonic sensor that's meant to represent a sensor. And this is our slave 1 with respect to the way that our SPI bus is addressed. The CPU is shown in the middle. That is our master, and on the right is VD003, which is a generic storage device, but I have it depicted there as an SD card, and that will be our slave number 2. The CPU, the objective of the lab is for the CPU to read sensor readings from the sensor, and then store them onto the storage device until we fill the storage device, at which point we exit the program. In this arrangement, the CPU will be sending addresses through MOSI to both peripherals. It will receive data through MISO from the sensor, and it will send these values through MOSI to the storage device. Now, as we previously presented, there are multiple ways to connect more than one slave to an SPI bus. We're showing the way that we're doing it in this lab on the slide. The master sends its outgoing clock signal, its S clock, as well as MOSI to both slaves, and each slave will drive a common MISO wire back to the master. That's problematic, and I alluded to this in an earlier lecture, because only one device can drive a wire at a time. So it is assumed that when one slave is driving MISO, meaning that it's setting it to 0 or 1, the other slave will detach itself from MISO using a tri-state buffer. The master will have a dedicated slave select wire for each slave. So what that means is that when we had 4 SPI wires in the previous lab, now we have 5 because only 3 of the 4 original wires are shared, and now we have to have a separate slave select or chip select for each of the slaves. Note that this is not actually supported with the built-in SPI interface of the 328 chips that we use in class. Of course, you could still do this through bit banging. We built a few challenges into this lab that we didn't have in the previous lab. The first is that the sensor peripheral, VD002, responds to each read request, or request to read data, sensor data, with 1 or more bytes that all must be read in one transaction. And normally it's going to be more than one. There could be, in fact, there could be up to 253 bytes. So as I explained before when I was talking more generally about doing multiple reads in one SPI transaction, the master is reading these bytes, is reading multiple bytes by driving the clock for n+1 times 8 clock cycles, where n's the number of bytes to read. The reason it's n+1 is because, of course, it sends the address first, and then it subsequently reads all of the bytes that the sensor has to send. How does it know how many bytes the sensor has to send? Well, in order for it to know that, it must first ask the sensor how many bytes are ready to be read by reading another register on the sensor called the data count register. This way, every time the master wishes to reach sensor data, it must read the data count register using a simple single read to exchange SPI transaction. And then subsequently, after it deasserts the chip select wire to end that transaction, it must perform a second SPI transaction to read the data register, which will then include all of the bytes that the sensor is ready to send. So this is a picture of a waveform showing that, and this waveform comes from a tool that Charles found that prints nice waveforms, and you can see that Charles also has annotated that as well. So this diagram shows two SPI transactions. You can see that by looking at the CS1 signal at the very top. It's high, means it's deasserted, and then it goes low to become asserted, and then back high to become deasserted, and then back low again to become asserted again. So you're seeing at least two transactions on slave number 1. Chip select 2 is never asserted, because that we're only, in this case, or what's shown here at least, is only interactions with the sensor. So the second chip select does not become asserted. You can see the interval, the amount of time spent on the first transaction is noticeably shorter than the second transaction. And this is because the first transaction is a single read of the data count register, and therefore there should be 16 total SPI clock cycles, right? That's 8 for the address and 8 for the data count. You can also see during the first SPI transaction that the MOSI line pulses twice. It's high for 2 cycles. That corresponds to the two 1 bits that are contained within the address for the data count register. While the MISO line is high for 3 consecutive cycles, because the data count register is actually 7, and that's the 3 1 bits from the value of 7. Then after the first transaction, chip select 1 deasserts. That ends the first transaction. It asserts again to initiate the second transaction that reads the data from the sensor. In this case, you can see that the MOSI line pulses only once, because in fact there's only one 1 bit inside the address for the data register. MOSI, would be is where the master is setting the address. And then the MISO line pulses several times over the course of 7 times 8, 56 cycles in which it is reading the sensor data, or in which the slave is conveying the 7 bytes of the sensor data. And sorry, I forgot to scroll to the right there. So let me go over that one more time. So we've got the first transaction is reading the data count. There are 7 elements that are reported. The second transaction is the data, and that is comprised of 7 bytes. The second transaction, of course, is 8 bytes in total, because the first byte is the address. Okay. So these 2 slides are showing the total operation, data read operation. Okay. So the third challenge is the way in which you store data into the storage device. Well, first of all, the CPU can only store 1 byte per transaction. So bytes read from the sensor will need to be buffered in the CPU. What do I mean by that? I mean that if you read, say, 10 bytes from the sensor, you can read those in 10 cycles. However, storing those 10 bytes to the storage device will take longer, because you'll have to, you can only do 1 byte at a time. You can't stream data into the storage device. The second issue is that the address that you use to store a byte actually is comprised of 2 separate components on the storage device. First is the page address. Why do we need a page address? Because the storage device is organized into blocks of 256 bytes called pages. When writing a byte to the storage device, CPU must specify the page it wants to write to, as well as the offset within that page, within the currently selected page. Thus, a write operation requires writing 1 byte requires up to 3 separate SPI transactions. Not exchanges, but transactions. You need 1 to specify the page, 1 to specify the offset, and a third to specify the byte that you want to write. On the other hand, if you want to write to the same address multiple times, you could actually do this in only one transaction after the initial byte. So in other words, once you set up the page and the offset, you can write the same byte multiple times with only one transaction. Or if you wanted to perform multiple writes within the same page or multiple writes to the same offset in different pages, then you actually need two transactions for each of those after the initial one. Okay? And it turns out that in this lab, we will be doing a lot of writing multiple times to the same page. So you don't necessarily have to do all three transactions for every byte that you write. Lab 3 requires that each multi-byte sensor reading must be stored into separate pages using the format that is shown on the slide. So each sensor reading, each page rather, starts out with a magic number in its first byte at offset 0. A magic number is a way to signify to a reader what the format or what the content of the page is. This is pretty typical whenever you store binary data to a file or to storage. The magic number is 11 in hex. The second byte is a sequence number, which is which sensor reading. It's basically just the page number is stored in there. So the first page you store, first sensor reading you store is 0, and then 1, and so on. The third byte is the number of data values, which is the number of bytes that you read from the sensor. And then the fourth value is going to be the first data value in the sensor reading, and then subsequent bytes will be the remainder of the reading, the bytes from the sensor reading. Okay, so if you read 10 bytes, for instance, from the sensor, then you will store the first byte at offset 3, and the other 9 in 4 through 11, or B, right? Okay, so that means that you can follow a fairly simple algorithm for this lab. Basically, you want to begin by reading and verifying the who am I from both slaves, which we did this for the one slave in the last lab. Then you need to read the number of available pages from the storage device, which is in a register called n page, number of pages. So basically what that means is you don't know when you start how many pages you have in the storage device. So you need to read that to know how much data you can store. In other words, you don't know what you're reading the capacity. Then you can set, you want to increment that by 1 because the number of pages is going to be 1 to 256, but that needs to be stored in an 8-bit value that's going to span from 0 to 255. So you're going to want to add 1 or increment the number of pages by 1. So in other words, if the n page is 0, that means there's 1 page, and if n page is 255, that means there's 256 pages. So you initialize page, which will be basically a counter to 0. While page is less than the number of pages, then you will repeat the following. You will load the data count from the sensor, and then you will then load the data into an array called sensor data. Then you will set up which page you want to write to in the storage device by setting the page cell register. And then you will set the offset to 0, followed by setting the data to 1, 1, because that's the magic number. You'll set the offset to 1, then set the data to page, the page number. And you set the offset to 2 and set the data to data count. So now we've got the 3 bytes that are needed for the header of each page. And then you'll have a loop that will iterate from 0 to data count minus 1. And for each of those, you'll set the offset to 3 plus I, and then set the data to the one element of sensor data at index I. Once you're done with that loop, you will increment the page and then continue with the while loop, or exit the while loop if that was your last page. So there's a few additional details in the lab sheet about what we expect in terms of the output from your program, but that's the gist of what we want you to do. So again, it's very similar to what we were planning to do in the lab with the actual hardware. We had a lab in mind where you would be measuring data from a sensor and storing it to an SD card. But since we can't do it on the physical hardware, we'll do it with these virtual components. So if you have any questions, as before, please feel free to contact us. All three of us are available for consultation over Blackboard Collaborate, and I think everyone's been very flexible about that. This lab will be due on Tuesday. I'll have another lecture for you on Monday where I will be covering reviewing I2C and assigning an I2C quiz, and possibly a lab at that time as well. So thank you, and good luck.